Alright, hello, I hope this is recording. I didn't like the way I explained a few things in lecture, so I'm going to redo it again right now. The first thing was we didn't really get enough examples of actual unit testing because we didn't have enough time. And so the first thing that I want to do is actually implement this double equals operator for linked lists and also implement some tests for it. So let's go back to the code from class. I made a copy of it in a folder called 1008 video instead. So let us go there and work on this operator equal equal, which takes another list that we want to compare to, compare for equality and value equality. So the idea is if I have two lists, like L1 and L2, let me go like this, make it small please, I want to draw. If I have L1 and that equals 1, 2, 3, and I have L2, I'm just drawing this Python style, and this is also 1, 2, 3, where these nodes, maybe I should write this, these nodes are in different places on the heap, even though they hold the same values. So even though they're in different places on the heap, they're still 1, 2, and 3 in that order, and we want to return true. So L1 equal equal L2 should be, what's a B? True. Just like that. So back to this code. The first thing that I did was just implement a stub, which is completely incorrect, but we're going to make it perfectly correct now. So this is going to return a Boolean, true or false, depending on whether or not those values were the same. So the idea is we need to iterate through each list at the same time, through both lists at the same time, and see if the values inside each node lines up. So the idea is I'm going to go through L1, start off at the first node, start off at the first node of L2 as well, and then keep on advancing. If those are the same, keep going. Otherwise, return false. Now look at the 2s. Are those the same? If those are true, keep going. Look at the next nodes. And now we're at the 3s. Are those the same? Keep going. And now we're at the end of the list, which is marked by null, so really null. Null PTR, right? And once we hit there, we know that we're at the end of the list for both lists, and we can return true, like they are equal. So that is what we want. So let's do just that. Let's start off a pointer for node n1 equals our head, and n2 can be others' head, so their head. And we want to make sure that they're still the same. So I'm going to go through them both and make sure that they're the same. So while n1 is unequal to null pointer and n2 is unequal to null pointer, we're going to iterate. So if they're the same, keep going. Check if their data values are the same. So if n1 dot info is equal to n2's info, we should keep going and keep checking. So if they're unequal, we should stop. Return false. They're different. And these are pointers, sorry. N1 and N2 are pointers, so we must dereference them before we get their infos. And that should be all right. Let's see, why is this unhappy? Cannot be used to initialize an entity of type linked list node. I don't know why it's complaining about that. We'll see what happens when we compile. Let's see. Let me actually try compiling right now, just to make sure something isn't going horribly wrong. Make test linked list. Dun dun dun. Linked list.h. There is no template named vector. Well, we need to tell it about vector over here, so include vector. Because we needed a vector here to use vectorize. and it's a standard vector. All right, and now it's warning me about this other file, and yeah, and now it's suddenly happy. So that was really okay what we were doing. So if they're true, we'll return false. Otherwise, keep going. Advance both pointers. So we'll say n1 equals n1's next, and n2 equals n2's next, just like that. That's the process of going from, we were first looking right here at these nodes, and now we're done, they were the same, we'll start looking at these nodes. Okay? We're doing that now, and eventually we're going to get to the end of one of the lists, because maybe, just maybe, there was like a 4 right here. And so one of the pointers is null, like we're at the end of this list, but we're still at a place in this list that has a value. So if any of them are null, that's what this is checking, if any of them are null, we'll stop the loop. Okay? So once we got here, at least one of n1 and n2 is equal to null pointer, and we better check now whether or not they both were, because if they both were, then everything was the same. If they're both null pointer, and see if you can convince yourself that this is correct. If they're both null pointer, then the lists were the same. All right? So if n1 is equal to the null pointer and n2 is equal to the null pointer, so they're both at the end of their lists, then we can return true. Otherwise, we'll return false, because one wasn't finished yet. One list wasn't empty, even though the other was. And the other was. There we go. So I think that is a correct implementation of this equality operator, but we don't even have to worry about that just yet, because we can test it and convince ourselves that way instead. So let's see. This is going to return. Now it looks like on line 41 I did some kind of mistake. Oh, yep. This was the copy constructor. I'll return this. I forgot to do that. Or the assignment operator, excuse me. There's that. All right, so now it's compiled and everything's fine, but we want to test this now. Let's test our double equals function. Okay. Now, let's do it this way. So void test operator equal equal. And if we go back to our slides, the way that we do unit testing is we make a class with the same name as the class we want to test, with test at the end, and then we put all our test functions inside. I was about to be lazy, but I'm not going to be anymore. So here we are right here. I'm going to make a class now called linked list test. Yeah, linked list test. And I'm going to put these functions inside. I'm going to make them all public. All right. I can't actually have those special characters like that. I'll just say EQ, perhaps. And it'll just be a void function. And here is how we will implement it. I won't do it separately this time. Let's make a linked list L1 and a linked list L2. And let's start them off with some stuff. First of all, if they're empty, this is one test. Test 1, empty lists should be equal. So I better assert now L1 is equal to L2. Better be true. So I'll say like assert L1 equal L2, just like that. And there's a, let's just make our own assert function actually. So void assert, it takes a Boolean value, B, and if you've never seen an assert function before, this function makes sure something was true. I'll actually call it assert true instead. Complains if not, because we want this to be true. This is our test case right now. We're asserting the fact that L1 should be equal to L2. Equal to L2. Okay. So if it's true, if B is true, then do nothing. That's what we wanted. Otherwise, I will say see error is like see out, but for error messages. See error include iostream using namespace std. See error your test, the test. Let's see. We should give our test a name. String test name. Test name failed. Okay, so we'll do that. Include string as well, because we want to use strings. New line. All right, there's that. Or maybe we can just say failed or passed, because that's kind of what Gradescope is going to tell you. Passed test name, or failed test name, sorry. And this one can say passed test name. And that can be the name of our test, empty lists double equals. So that's one test, and it should be true, this assertion. So if this is true, we'll get a line printed out to us. Yes, these things passed. And I might as well just see out everything now, because it's not really an error message sometimes. All right. So in my main function now, instead of doing all these weird things and just testing functions, I will make a linked list test object. These are my tests. And so I'll run test operator eq, and this will run our test for the equal operator on linked lists. And we should say, we should get something that says passed right now if I compile and run this. Make, and then run test linked list, and yes, our first test passed. This is good. So let's keep on using L1 and L2. Let's add one thing. So L1.append 1. Right now the lists are different. So let's assert true. L1 is equal to 1, L2 is equal to the empty list still. So this is not true, that equality. So we should assert that. And now let's add 1 to L2 now. And so these are 3 test cases. So each test case is one of these assert functions. And we'll assert true this final one. Oops. Let's get rid of these comments because these ones down here are not the same anymore. So they're both like that, and they both are equal. So in theory, if we implemented our function correctly, we'll see passed. Sweet. And you can implement as many test cases. You can add as many test cases as you'd like. Definitely enough to convince you that your implementation is correct. So the corner cases are usually something's empty, something's unempty, and those are all the things that I've tried, all those combinations. So you can definitely try more because maybe there's more to test. But I think this is a good start for our testing of our equality operator, and hopefully that helps make unit testing make a lot more sense. All right, so that is that. And now I want to go down to this rule of 3 thing. So the idea is linked lists are a bit fancier than the types that we've been considering already up until this point in the class. Linked lists, let me just start writing all this stuff. Linked lists allocate memory from the heap. This changes things. In a good way or a bad way, depending on how you think about it. So now, our constructor starts out the list empty. Our constructor needed to be default constructor overridden because we needed to start the lists out as empty lists by making head and tail null. Right? Null pointer. And that was very necessary. So now we need to worry about these things as well, because the default behavior of these 3 things, the destructor, the copy constructor, and the copy assignment operator, is not going to be what we want for linked lists. And I'm going to, at least right now, I'm going to re-explain the default behavior. So let's pretend we had a linked list first. So here's our linked list, L1, and it lives maybe on the stack. Here's our L1, and it has a head and a tail. I'll try and draw them in like this, head like that, and a tail like that. And these are all pointing to nodes, because if it's a non-empty linked list, that is, on the heap, which have a info and a next. So 1, 2, 3 maybe can be our list. And so head will be the first node. Oops, I overshot that arrow, excuse me. And tail would be the last node. And it would look just like that if we had a size 3 linked list right now. So L1 is the name of our linked list object. So the type of L1 is linked list. And these are all nodes sitting over here on the heap. This is a node. Maybe I'll say it for this one, and then also be like, these are both also nodes. Okay, so I'll do that. Oops, I want to turn this off for myself. I don't know if you can see it. All right, so that's that. Eee, that's bright now. So that's how we start off. But say we're done. Say we had a function. Say L1 was in the main function even, and the main function is done with. So we're going to get rid of L1, which means its destructor is going to be called. The default destructor doesn't do what we want because it will only get rid of L1's memory. Head and tail are primitive types, so those are just pointers, and so it's not going to go and follow them and try and get all these things at the heap. Even if it did, it would miss out on this too, wouldn't it? So we don't like the default behavior, and that is the default behavior of the destructor. Default destructor behavior is this. It takes it calls the destructors of all the member variables. But head and tail are what are known as primitive types. And you can think of those as like ints, bools, pointers, really anything that's not a class, non-classes. And so they don't really have a destructor. And so nothing really happens other than their memory gets reclaimed. The memory of the member variables of head and tail themselves get reclaimed. And by that I mean this box right here. That's going to be reclaimed. That's going to be reclaimed. But the things that they're pointing to will not be reclaimed. But not the things they're pointing to. Okay? So that is the default destructor behavior. And we don't like that because it forgot about all the nodes. So if this goes away, these all stay on the heap and we lost them. Okay? We lost them and they are memory leaks, in fact. And let me now write that. And go over here and talk about this iClicker question. So what it does is it makes a vector that we're comparing against eventually. So vexp is the vector 1. What is happening? Sure. vexp equals, you can think of it as an array holding 1. And then we also make a linked list, LL, which holds just the value 1 because we append to it. We add one thing to the end of it and it starts out empty. So LL equals the list containing 1. And we end up creating another vector called vact, which is the vector form of that list, LL. All right? Because we made a function over here that transforms a linked list ourselves into a vector of ints. Okay? So if I go back to the slides, and now I'll say that vact is going to be whatever LL is, which is the list containing 1, in vector form. So it's going to be the vector containing 1. All right? And so vact is going to be equal to vexp totally. And so this is going to print out past. But what's going to happen is LL, oh man, it's a local variable. Which means it's going to go away. Its destructor is going to be called. And we're assuming a default destructor. The copy constructor and the copy assignment operators are not being used anywhere in this code. So the destructor is going to be called right down here, right as it tries to return, this testing function tries to return. And so we're going to lose access to that heap location because here we have LL. It has a head and a tail. Those are weird L's, sorry. Head, tail. They both point to the same thing because it's a node containing 1. The first and last node is that one node. And when LL goes away, its default destructor gets rid of head and tail, but this is still sitting on the heap. Still on the heap. The default destructor knows nothing about it. Okay? And that is why we want to change this. And also, this is why it's a memory leak, because the only way that I had access to this place on the heap right here was by following head, by following tail. Once I got rid of LL, I got rid of the only way I could access this. This is why it's a memory leak. This is a memory leak because I lose the only way of accessing this variable, this node on the heap. Okay? Because I could have followed those pointers, but I just got rid of those pointers. Now, these last 3 slides talk about the default behavior of the copy constructor and the copy assignment operator. So, the copy constructor, what that's going to do, by default copy constructor, is it's going to call the copy constructor of all the member variables. Calls the copy constructor for all the member variables. And I went and implemented this in class. that is this guy right here. So here is our copy constructor. It takes another linked list and it sets, using the constructor syntax, because we're calling the copy constructor, the head to be the other head and our tail to be the other tail. And this is not what we want, remember, because it does not duplicate the heap variables. And this is going to be an issue for us because of this reason. So let's see if I can go right back up to where I drew the first list, because this is a very pretty list. And I want to do something like this. Can I select both of these? Yeah. I want to copy all of this. All right, let's see if it'll paste down here. No clue if it will. Yeah, okay, that's beautiful. I lost a few things, but we'll fix it. We'll fix it. Gonna get rid of that. Get rid of that. Gonna get rid of that. All right, so this is L1, and forgot part of that K. So here's L1, and let's say we want to do something like linked list, because this is how we call the copy constructor. L2 made from L1. Okay, so that'll make an L2, and it'll set its head and tail to be the same things, because that's what the default one does, the same thing as L1. So let's see if I can zoom out here, because this is what's going to happen. It's going to set the head to be this. It's going to set the tail to be that. But that is an issue, because now if I do something like, let's see, this isn't good, because now if we say L1.append 5, or maybe 4, just to keep on going in the same direction, this is what's going to happen. We're going to make a new node for L1 to see. It's going to be 4 and null, and L1's tail is going to change to be this. But head and tail for L2, untouched. But if you were to follow now, from the head onward, you would find this 4 node, because it's reachable. And L2's tail is not really the tail of this list anymore. What you wanted to happen didn't happen. What we wanted was this. So the above happens. Now L1 and L2 are interconnected in a very weird way. What we wanted was this. Whee. Here we go. On the stack, maybe we have L1 and L2 again. So on the stack, let's say we have L1, and it had the exact same stuff. So it had a tail, I'll just say H and T to make it shorter for me. And 1, 2, 3, just like that. When we called the copy constructor, what we wanted to happen was this. We make an L2 with a head and a tail that, hey, yes, pointed to nodes 1 and 3. The nodes should be the same, but they should be separate, brand new nodes made on the heap again. And this is what happens when we say linked list L2 made from L1 as a copy. This is what we want to happen. We want an exact copy of L1 with all the same nodes and things like that. Still has 1, 2, and 3, but they should be separate from the nodes of L1. Okay? In L2. So that is the key difference. It's either, oh man, they're the same, that's the default behavior. The behavior that we want, however, is we want it to copy those nodes. So like copy the nodes. not just reuse them, because that makes weird things start happening. Okay? And so stack and heap looks like that. And that is the copy constructor. All right, back to the slides one last time. The default copy assignment operator now does exactly the same thing almost. So here's, again, that same kind of thing. Instead of 1, 2, and 5, I've been using 1, 2, and 3. Why not? Make an L2 list and then set its stuff equal to L1. So the default behavior is going to be this. The default copy assignment operator, again, we wrote in class, it's going to call the assignment operator on the member variables and return itself like it normally does. So the default assignment operator, and yeah, it's copy assignment operator, does this. Calls the copy assignment operator on all the member variables. So if we do what was in the slides, make L2, and then set it equal to L1, these two lines are going to do this. Let's say we had L1 again. Gosh, I want to try and copy this as much as I can, because that is a nice time saver for me. Stack and heap. Here's L1. We missed some things. L1, come on, head. There we go. Head is 1, tail is 3. And then I'm going to make, in 2 lines, linked list L2. What that does, remember, is it makes an empty linked list. And an empty linked list has a null head and tail pointer. So I'll draw that like this. So that's what that first line does. And now when I say L2 equals L1, what's going to happen is we're going to set head and tail again. We're going to reset it. So head is now going to be L1's head. And oh man, do we have the same problem again. Tail is going to be set to L1's tail. And hey, we have the same issue. So again, the idea, what you want to do is make copies instead. All right, so let me see if I can draw this again with the right answer in mind. Zooming on in. All right, there we are. So what we wanted was, oh no, not that, not that. We wanted to make, when we did this, brand new nodes just like this. 1, 2, 3. And then set head to be that one and tail to be that one. So again, we want to copy these nodes again. All right, so that is the copy assignment operator that we want to do. And a possible way to implement this would be using the append operation. And so I should also say this here. One way to implement this is via the append function that we implemented in class, because then we can just iterate through this first list, see the 1, append it, now we have a 1 node, see the 2, append it, now we have a 2 node, see the 3, now we have a 3 node, just like that, using the append function. And it sets the head and the tail properly for us as well. So that's what we want there. There is one key detail of the copy assignment operator that is not apparent. What if L2 was not originally empty? So again, L1 can be 1, 2, 3, not 1, 2, 5. Here's L2. We're going to now add 10 and 20. And then we're going to use the copy assignment operator. So again, the default behavior is just reset the things. So here's what's going to happen. I wonder if I still have that thing copied. Oh, that's beautiful. All right. So L2 equals L1. So some things have changed. That's changed, that's changed. I want to move this on down now because I want to add some more code. I guess I'll erase that. So we're going to append 10 and 20. L2.append 10. L2.append 20. And then we want to do L2 equals L1. And this is the subtle difference between the copy assignment operator and the copy constructor. So L2, after these two lines, if we're sitting right here, this is what L2 is going to look like. It's going to make some new nodes with 10 and 20 on the heap in this order. Head's going to be set to this, tail's going to be set to that. And now the default copy assignment operator is going to just copy over. Head's going to change. So now I'm executing this line. I'm executing the default copy assignment operator, that one. Head's going to change, and tail's going to change. They're going to point to L1's head, L1's tail. And oh man, do we have that same problem, but now we also have a memory leak. And we also have a memory on top of that. Well, that really sucks. So now we cannot implement the copy assignment operator the same way as the copy constructor because we might have some things from the beginning left over. So what we need to do instead is the use of append is still a good idea. And again, this is a memory leak because we lose access to these nodes. We have no pointer going to them anymore, right? That's a memory leak because we have no pointer going to them. There is no longer a pointer going to them. Okay? Use of append is still a good idea, but we should also clear the list, our entire current list, before we use it. Okay? So the idea is, what we need to do instead, if I copy all this one more time, we're going to take all this, and oh man, are we going to change it? So we don't like that, we don't like that, we don't like that. So going back to right here, after this line is executed, we have head and tail for L2 set up like this. Have not called the copy assignment operator yet. So now, the idea is that we want to, well, I don't want to have this anymore now, do I? The idea is that we want to make copies of these nodes, totally. But we also want to clear these nodes off the heap. Delete that, delete that. So I'll erase them now to represent the fact that we've deleted them. And we should also maybe set head and tail to be null so we can use that append operation because this is now an empty list for all intents and purposes. It's exactly what it means to be an empty list. The head is null, the tail is null, and there's nothing floating around in the heap that is a leak anymore. Okay? No more. That is not a good more leaks. That's beautiful. Okay? And so now we will call our, we'll do the rest of our copy assignment operator. That was the first step of the copy assignment. That is the correct version. We cleared ourselves, and then we'll append those same nodes. 1, 2, 3, just like that. And of course, head and tail, after that process is finished, will be set just like that. And again, we've copied after we cleared. And so that is a lot more in-depth example. I'll try and repeat this again on Thursday of just the way that these default constructors behave. And the idea is linked lists dealt with heap objects, things that we manually allocated for ourselves. And that meant that we had to manually worry about those things as well. And it turns out that this rule of 3 is a really good rule of thumb in that we noticed at the very beginning that the destructor that we get by default is not the right one. So we had to change it. And then, oh man, did we also notice that the copy constructor and the copy assignment operator, those also didn't give us what we wanted. Usually, it's going to be the case that all three of these need to change if you notice that just one needs to change, and that is what the rule of three means. And linked lists are a great example of that. So yeah, I think now we've talked about the default behavior. I'm going to give you a copy of all this stuff, of these notes that I wrote. You should have them in like PDF or something. And we talked about what we wanted instead, and I've given you some some comments in the code as well of how to override these methods and implement them the way that we would like them to be implemented. A lot of the time using the actual new and delete, or just the delete operation, because we're going to have to clear some things, and then we also want to use append for this last case. All right, and yeah, for the destructor, you have to definitely delete everything. So kind of the first step of the copy assignment is to do the same stuff that you would have done in the destructor. All right, now I think I'm just rambling, and that is exactly what we wanted to do today, but I didn't have enough time. So thank you for watching this, and I will see you on Thursday. Let's see if I can figure out how to stop it.